All right. In this lecture, I'm going to talk about how frequency factors come about. So, frequency factor is part of the rate constant. So, we typically think about the rate constant following an Arrhenius model, where the rate constant then is going to be equal to a frequency factor times an exponential term, which is a function of the activation energy and also the temperature of the reaction. So in this expression, this term here is the exponential term. And this term, A of t, or usually just we refer to it as just A, it is usually a function of temperature, but a lot of times we ignore that. This is going to be the pre-exponential term. And we also call it the frequency factor. And I say that we ignore the temperature dependence of this term because it's usually not as strong as in the exponential term. So the exponential term is an exponential function of the inverse of temperature, but regardless that it's inverse, temperature still has a significant effect on the exponential term. The pre-exponential term, the dependence on temperature is usually less than that, maybe temperature to the minus 1/2 power. So because of that, we usually ignore the temperature dependence in the pre-exponential term, but it is there. Okay, so the frequency factor. So this quantifies the number of opportunities for a reaction to happen. And the best way I can explain that is that if for a reaction to happen, molecule A has to combine with molecule B. Maybe let's say for a reaction to happen, molecule A has to react with molecule B. The frequency factor is going to quantify how frequently molecules A and B come into contact. So how many opportunities are there to react? The exponential term is then going to scale that total number of opportunities by the probability of occurrences that have sufficient energy to promote the reaction. So the exponential term is kind of like a probability. So the exponential term is going to scale the frequency factor by the probability that a reaction will occur given the energy of system. All right, so there's several ways that we can estimate frequency factors. Some of these are based off what we call transition state theory. In transition state theory, the rate constant is going to be equal to some term, and I'll explain that in just a minute, times the exponential of the change in free energy between the transition state and the reactants divided by Kb times T, and I'll explain what that is also in just a second. So if we break this down, this is going to be, we can extract out both enthalpic and entropic contributions to this term. So what are these different pieces? This delta G term here, this is going to be the free energy of the transition state minus the free energy of the reactants. I've written a sum on reactants and no sum on transition state. I'm kind of thinking about this as a combination reaction. You have two molecules come together. The transition state is then going to be one species, but there's going to be two reactant species. In general, we just like a chemical reaction, we need our mass to balance, our atoms to balance. So this may not be a perfectly general formula, but that's why I've written it this way. Okay, so other terms. Kb is Boltzmann constant. And it's equal to the gas constant in energy units. So not in pressure volume units, but in energy units, divided by Avogadro's number. So one value of that would be 1.381 times 10 to the negative 23 joules per Kelvin. H is Planck's constant. It is going to be equal to 6.626 times 10 to the negative 34 joule seconds. So if we take these two numbers and put them into this equation, this term here is about on the order of 10 to the 12th or 10 to the 13th under ambient conditions. We'll say, so kBt over h is 10 to the 12th to 10 to the 13th, and that would be in units of per seconds at ambient conditions. So you think about that leading up to a total number of occurrences. This is what this is saying, is that based on this particular term, it's putting us on an order of 10 to the 12th or 10 to the 13th occurrences happening per second. All right, so if we follow this a little bit further, if we take our equation here and we want to reduce this into a frequency factor and an exponential term, we could say that this is going to be equal to a of t times exp negative delta h over kBt. So this here is our exponential term. Notice I've written the change in enthalpy between the transition state and the reactants here, and we're used to seeing an activation energy. The activation energy, what that really is, it's going to be the change in electronic potential energy between the transition state and the reactants. It's going to be very close in value to this this delta H and the change in enthalpy. And in reality, if we were going to take which one is correct, it's this equation here, the change in enthalpy. So this here is going to give us our exponential term, and then our pre-exponential term would be what's left, and that's going to be this contribution right here. So our pre-exponential term in this case, or under this transition state theory model, is going to be kBt over h times the exponential of the change in entropy going from transition or reactants to transition state divided by the Boltzmann constant Kb. Okay, so now we can quantify this based on what we have going on. So let's look at a couple of different scenarios. One scenario, which may be easy to conceptualize, is say you have the reaction A goes to B on a catalyst surface. Let's say reaction A goes to B. So we're going to convert A into B. So what's happening here, A is reacting to form B. What happens here when this reaction occurs, if I have my energy or free energy, we'll say energy units, and here I have what we'll call it a reaction progress. You may also see reaction coordinate. I may have some sort of energy diagram that looks like this, where this energy right here is the energy of absorbed A, here is the energy of absorbed B, and here is the transition state. Oftentimes we will denote this with this double dagger symbol, a dagger or a double dagger symbol. But this is going to be our transition state. I'm just not doing well at writing that today. Transition state. Okay, so now we want to look at basically the change in free energy between this piece here and this piece here. So let's think about what the contributions to the entropy of those two different states would be. So A, that has electronic, vibrational, translational, and rotational contributions. To entropy or energy or free energy. Of those, we tend to say that the electronic contribution to the entropy for almost all species is close to zero. So there's not much electronic entropy. We also say, and here, let me actually fill that in. So that's true for most species. On a catalyst surface, we can say two things. We can say that species A is fixed, and therefore it has limited translational and rotational entropy. We could also say that species A and the transition state have similar translational and rotational entropies because they are both fixed to the catalyst. Let's, for the sake of ease, say on a catalyst surface, species have limited translational and rotational entropies because they are fixed to the surface. So what I mean by fixed, the species here forms a chemical bond with the surface, right? So it is going to have limited translational mobility because if it tries to move along the surface, if it tries to diffuse across the surface or translate, for example, it's going to have to break that bond. Similar with if it wants to rotate around, it's going to have to alter the way it's bound to the surface. And those have energy penalties, so because of that, species don't really do that. So both species A and the transition state, so we'll say all of this, all of these assumptions are also true for the transition state. So therefore, one way to estimate delta S is going to be delta S of, here, and let me do a better job. So I'm going to say all of this is true for the transition state. I'm going to denote transition state TS. So I would say here, and I don't need a delta here. Oops. I am just not getting it right today. So basically, we're going to estimate this. Let me make it clear that we're going to estimate this. We can estimate this contribution, or the change in entropy, as equal to the change in vibrational entropy between the transition state and the reactant species. And again, this is just one model. There is going to be other models, so this doesn't explain every single circumstance, but it can explain, for example, surface reactions. Okay, so let's consider another process. So here we'll consider an adsorption process. So I have a molecule in the gas phase, and it's going to react with a catalyst surface to form an adsorbed molecule, or I guess it's going to adsorb to the catalyst. I shouldn't say react. It is going to form a chemical bond, but when I say react, I worry that I also give the impression that this molecule is going to react itself. But what I'm really talking about is, for example, species A. Maybe I can write that. So this is my A gas molecule forming adsorbed A. So I'm looking at like this reaction. A gas plus star goes to A star. All right, so what I have here, I have a gas molecule. So this is gas molecule. It's a 3D translator. What this means is that it has three-dimensional degrees of freedom. So it can move freely in all three dimensions. So it's a gas phase molecule. It is not interacting with any other thing. It's not interacting with other gas phase molecules. And it's from the vantage point of this gas molecule, there is nothing else in the universe except for it. So it's whizzing around in the gas phase freely. It is completely free to move. There is a theory that an adsorption process essentially takes away one of these degrees of freedom. So in the process of adsorption, I should have drawn that a little bit shorter. So I have process of adsorption. What I would have is species A coming and it's interacting with the surface, and I kind of drew that as a squiggly line to kind of show it's not like a fixed bond, right? So it comes into like the potential field of the surface and it's interacting with the surface, but it hasn't formed a chemical bond yet. And so the assumption here is that A can translate along the surface. So it can translate in the lateral dimensions of this surface, kind of freely in these two dimensions now. So it can't leave the surface without desorbing, right? If it desorbs, though, it's gas phase A, not adsorbed A. But it, as long as it's on the surface, it has now 2 degrees of freedom. So the hypothesis here, or the model that we're going to use, is going to be that this is a 2-dimensional translator. So we'll say here, that is free to move in 3 dimensions. This is free to move in 2 dimensions. And again, this is a model. For this model to be perfectly correct, what would have to happen with this surface here would have to be perfectly featureless. And I think there's other ways that we could describe what's going on here, but I think maybe this is the most conceptually easy. So in this model, we labeled this 2-dimensional translator the transition state. This species is eventually going to find a site where it really likes to bind, and it's going to form this chemical bond. So a chemical bond here, and it's going to become stuck. So this here would be our adsorbed molecule. And we could say it is 0 degrees of 0 degrees of translational freedom. That may or may not be correct, but as for the sake of making a concept here, explain the concept or illustrating it, let's say that that's the case. So now we want to go back to our transition state theory formalism and develop a rate constant for this process. And we're going to use this A equals KBT over H times the exponential of delta S dagger over KB. So that means we need delta S dagger between, we'll say, now here we are technically going to have multiple contributions. So we would say we'll take the translational entropy for A gas, and actually I'm writing this backwards. So we want the transition state piece first. So I would say translational for our 2D translator. Plus our rotational. This 2D translator would have rotational mobility because it has not formed a chemical bond with the surface, so it's free to move, it's free to rotate. The problem, if once it forms that chemical bond, it can't rotate because there's a large energy penalty to do so because it would have to rearrange the bond it made with the surface. But until it makes that bond, it has rotational mobility. So we would say, we would include that in our contribution here. We'd also say it has vibrational entropy, vibrational degrees of freedom. I'm going to skip here the electronic because we've said that's usually small. So now I want to take the same things for my reactant species. So I would say a gas, translational, rotational, vibrational. I can now make the assumption that STS rot equals S of the gas phase molecule and STS Vib equals S of the gas phase molecule. That's probably not exactly true, but it's probably a reasonable assumption. And so then this says that my energy, my transition state energy, or entropy, sorry, the change in entropy from my reactants to my transition state is going to be vibrational contributions only. And I'm sorry, this should be translational. I'm in the wrong model here. And so basically what I have here is the change in entropy going from a 3D translator to a 2D translator. And that's probably what I was supposed to write down here. I'm kind of off in my, yeah. So we can just write that. We can say 2D translator minus 3D translator. And these are free particles. So basically, if I know how to quantify the entropy of 2D and 3D translators, I can quantify that. What I end up arriving at is that this term A then becomes identical to the equation for the flux of gas molecules to the surface. And I'm not going to go through that derivation. You can probably find this derivation in a physical chemistry textbook, but that's where this term comes from. So then this flux here is going to be equal to the kBT over H times the exponential of S 2D translator minus S 3D translator divided by the Boltzmann constant Kb. In this equation for flux, lowercase m is the molecular mass. So what is the mass of one molecule of whatever gas phase species you're talking about? If we were to quantify this out, the flux of gas molecules is going to be about 10 to the 20th times the pressure, or actually the partial pressure, when the pressure is given in torr, or millimeters per mercury, or millimeters of mercury, at 300 K. And that's going to be per centimeter, per square centimeter per second. So quite a large flux of gas molecules even at 300 K. So this is our frequency factor here if we are talking about an adsorption reaction and using transition state theory. Based on the assumptions that we made, this is the same frequency factor that would result if we had used kinetic theory of gases. So kinetic theory of gases is also called collision theory. If we want to see in a simulation of what that looks like, let me see if I can. Oops. Yeah. Well, I'm not able to click this. Let me try one thing. Nope. Well, if you have a chance, you can view this simulation. It basically is a simulation of gas molecules. And the gas molecules are in a box, and they are colliding with each other and with the walls of the box. And that essentially is collision theory, or I'm sorry, kinetic theory of gases. So kinetic theory of gases assumes that gas molecules are ideal. When I say that, what I mean is that they do not interact with each other. They also do not interact with the walls of the container. It also assumes that gas molecules are in constant thermal motion. And that they obey Newton's laws of motion. This means that their motions are classically defined, or defined by classical physics, not quantum physics. It also assumes that collisions are perfectly elastic. It also assumes that the average kinetic energy of the gas molecules is directly proportional to temperature. So in other words, it assumes that the speed of the gas molecules depends on the temperature. If the temperature goes up, the average velocity or speed, and let's say speed. I guess I could be getting it wrong if I say that, but I think that speed is the correct answer here. The temperature goes up, the average speed of the gas molecules also goes up. Under ambient conditions, so these gas molecules are moving around really quickly. Under ambient conditions, the average speed of the gas molecules is about 1 kilometer per second. So they travel quite fast. Okay, so under kinetic theory of gases, we can estimate the collision frequency of an ideal gas molecule with a flat surface. We do this using the Maxwell-Boltzmann distribution for molecular speeds. Again, I'm going to forego the derivation. You can probably find it in a physical chemistry book. But the expression that we get is similar to above. We now have here an area term in our equation, but pretty much everything else is the same. You notice that when we looked at, the flux equation here, there's no pressure in the numerator. However, if this is a rate, or part of a rate constant, the pressure term there is going to come in be part of the reaction rate. So we would take the rate constant times, if we're looking at this reaction here, and we're going to write this, we're going to write the rate of this reaction. That would be, so we would say RA star, for example, is going to be equal to the rate constant times the pressure of A, or the concentration of A, times the free site coverage. So that's where that pressure term comes into play in this equation. If we're talking about a molecular flux, so we're not necessarily talking about a rate constant for a reactor design problem, the whole answer here is going to be, it's going to have that pressure term in there. If we're going to use this as a rate constant, we're going to take that part out because it's going to become part of our reaction rate anyways. You see also we have this area term here, whereas it didn't exist above. If we're looking at this, or we're trying to use this as a frequency factor for a catalytic reaction or an adsorption reaction, what we're going to do is replace this area term here with the site density. For some reason, the site density is sometimes denoted with L in brackets. I don't know why. What this L in brackets is the total concentration of surface sites, and it has units of sites per area. So you see how putting this here is going to basically replace this area term in the numerator, and it basically gives us the flux onto a catalyst site. This value here, the site density, the total site density, that's usually known. So for example, on a transition metal catalyst, the site density is equal to 10 to the 15th sites per square centimeter. So that is an adsorption reaction, two different ways, one using transition state theory and one using collision theory. Another, we can also use, however, this kinetic theory of gases for homogeneous gas phase reactions. There is a development of this on the Fogler textbook website. So again, I'm not going to go through the derivation. I'll just give you the final result. We get an expression for the frequency factor that looks like this. In this equation, the sigma AB term is going to be the collision diameter. So if two molecules, A and B, are passing by each other, what diameter is required for them to collide? Mu AB is the reduced mass. I should say the reduced molecular mass. Of molecules A and B. I believe that is, if you sum the molecular masses of A and B and divide by the square root of the product, but don't quote me on that. But that quantity, the formula can be looked up. Under ambient conditions, gas molecules collide with each other about 10 to the 10 times per second, and frequency factors in collision theory are about 10 to the 14 cubic angstroms per molecule per second. So notice here that we have the units on this frequency factor is going to be volume divided by molecules per time. This is for a bimolecular reaction where you would have two molecules colliding with it. So if I was going to write a rate here, or a rate law, so we would say, maybe we're looking at the reaction here. I have A, and then I have B, and these are going to come together and collide. And maybe what they're going to do is form C, and these are all gas phase molecules. I could say then that the rate of formation of C is going to be equal to some rate constant times Ca times Cb. Notice that this rate constant has perfect units for that. It's going to be volume per molecules, which I could also write as moles per time. So if I multiply that by, or I guess getting ahead of myself. So basically what it has is units of inverse concentration per time. So I have 1 divided by concentration per time. And so I multiply that by concentration squared, and I get moles per volume per time, or concentration per time, which are exactly the units on rate. All right, so that's gas phase, or homogeneous gas phase reactions. We could do the same thing for liquid phase. It's a little bit different, and actually the development is more complicated. Frequency factors in liquid phase are based on molecular diffusion. So in the liquid phase, getting molecules together, you don't really have these molecules whizzing around colliding into each other. In a liquid phase, molecules are very aware that there's other molecules around. There's lots of them. So it basically has, the frequency factor is basically going to quantify how they come into contact. So if you think about liquid phase molecules, they have some amount of structure to them, maybe not as organized as a solid, but they are all interacting. And what they do, for example, is, I don't really have a good one to draw here, but they are going to kind of bump into each other. So they bump into each other. These are called, when they do this, it's called an encounter, or a molecular encounter. So when we develop and I guess I've written that here, so when we develop the frequency factor for a liquid phase reaction, it has to do with the diffusion of the molecule and how often it is encountering molecules around it. So basically, if I take all of this together, what we see is that the model for the frequency factor is based on the physics that govern the molecules and how often they come into contact, which makes sense given that the frequency factor quantifies the total number of possible opportunities for a reaction to occur.